Okay, let's dive into something pretty fascinating today. We've got this stack of sources looking at, well, keeping animals comfortable in barns.
Right. Seems simple on the surface.
It does, but hidden inside is this surprising link to something you might be wrestling with in math class right now, differentiation.
Exactly. And this deep dive, it's really about bridging that gap, isn't it, between this abstract math idea, derivatives, rate of change, and a very real world, very practical application in farming.
Yeah.
What we're aiming for is to pull out from these sources how understanding not just the temperature reading, but how fast it's changing. Well, how that can make a huge difference on the farm.
And the sources set a great scene for this. They talk about places like Malaysia, think about the agricultural mix there.
Oh, absolutely. It's incredibly diverse.
Mm.
You've got massive poultry farms, cattle integrated with oil palm, rice, tropical fruits, rubber, cocoa.
It's this really complex, interconnected system.
Mhm. And in a setup like that, managing one piece, like the environment inside a barn, can ripple outwards,
Hmm?
affecting nearby crops, water use, everything.
Totally. So the big aha moment we're shooting for here is to show you how these math concepts, the ones you're learning, are actually powerful tools. Tools for solving real problems in farming, helping animals, protecting crops, building a more secure food future.
It's prediction in action,
Mm.
really not just theory scribbled on a page.
Okay, so let's unpack the basic problem then. Why isn't just knowing the temperature right now enough? Why the focus on change?
Well, the sources really highlight this livestock, especially the vulnerable ones, like young chicks or, say, high-producing dairy cows. They're incredibly sensitive to changes.
Oh,
It's not just hitting a specific high temperature, but how quickly you get there or how fast it drops. That rapid shift is what causes a lot of the stress.
so like a sudden heat spike feels worse than a gradual warm-up, even to the same final temperature?
Precisely. That rapid change, even if the temperature itself isn't technically extreme yet, it can kind of shock the animal system. This quick flux is a huge trigger for heat stress, especially somewhere humid like Malaysia.
And heat stress, it's not just about feeling a bit hot, is it? The sources detail some serious stuff.
Oh yeah, serious consequences.
Right.
Animals eat less, so growth slows down, or milk production drops. It can mess with fertility, weaken their immune systems.
Making them more prone to getting sick.
Exactly. And in bad cases, it can even lead to death.
Wow.
And, this stress on the animals, it doesn't stay contained in the barn. Sick animals need treatment, resources that might affect plant health nearby or compete for water needed for irrigation.
Hmm.
Plus, heat changes how manure breaks down, which
Yeah.
matters if you're using it as fertilizer. It's all connected.
Okay. So the rate of change, how fast the temperature moves, that's the key predictor for these potential problems.
That's where the math comes strolling in, yeah.
Right. Differentiation.
Instead of just tracking T, the temperature, we look at how T changes over time. That's the first derivative, dt dt.
Which tells us the speed, right? How many degrees per hour or per minute it's climbing or falling.
You got it. A big positive dt dt means it's heating up fast. A big negative one, cooling rapidly. And this number, this dt dt, it's like an early warning flare.
How so?
Well, even if the temperature is still okay, maybe it's, 75 degrees Fahrenheit, perfectly fine. But if dt dt is really high, it tells you, watch out, we're heading towards trouble fast.
Okay, that makes sense. And then the sources also mentioned the second derivative, dt dt. What's that add?
So that's the rate of change, or the rate of change.
Okay, like acceleration.
Exactly like acceleration. Is that rapid warming trend getting even faster? Or is it maybe starting to slow down, to level off?
Yeah.
Looking at this second derivative gives you a more nuanced picture of the trajectory.
Ah, I see. So you know not just how fast it's changing, but whether that change is speeding up or slowing down.
Right. And that gives you an even earlier, maybe more confident reason to act predictively.
Okay, that's where it feels really powerful. You're moving from just reacting when things get bad to actually predicting it before it gets bad.
That's the goal. By tracking these derivatives, a farmer, or more likely an automated system, can spot these problematic shifts way earlier than just by watching the thermometer needle.
It allows for proactive steps.
Totally. And that has benefits all over the place, starting with the animals, obviously. Less stress means healthier animals, better productivity, more milk, faster growth, you name it.
And you mentioned the knock-on effects earlier. Does managing the barn climate better help the surrounding crops too?
It can, yeah.
Yeah.
Extreme temperatures, especially those rapid swings, can influence pests and diseases that affect both the animals and the nearby plants. So keeping the barn environment more stable can help stabilize the microclimate around it a bit.
Interesting. Sort of slows the spread of temperature-sensitive problems.
Potentially, yes. It contributes to the overall health of that farm ecosystem.
What about the bottom line, the financial side?
Well, less stress, fewer sick animals, lower death rates, consistent production. That all directly cuts financial losses. Avoiding a major heat stress event saves money on emergency measures, too.
Right.
And interestingly, the sources also mention financial weather derivatives, a completely separate thing, but related. It's a financial tool farmers can use to hedge against losses from bad weather. Just shows how critical managing these environmental factors is for stability.
And this kind of detailed monitoring must help with resource use, too, like energy.
Oh, absolutely. If you know the rate of change, your ventilation, your heating, your cooling systems, they don't have to just be on or off.
Ah, they can be smarter.
Exactly. They can respond proportionally.
Hmm.
Fans only need to really ramp up if the temperature is rising quickly. They can adjust based on that DTDT value. It saves energy, fits right into that whole precision agriculture idea.
Okay, so practically speaking, how does this actually get set up on a farm today?
It starts with good sensors. Accurate temperature humidity sensors. Placed strategically. You need them high, low, near vents, maybe different zones in the barn.
Spread out.
Yeah. And some sources even talk about wearable sensors on individual animals. That could give you body temperature changes even earlier than sensing the air temp.
Wow. And all this data has to be collected constantly,
Right.
wirelessly.
Right. Collected, transmitted, and then fed into software. That's where the calculus happens. The software crunches those numbers, takes the real-time temperature stream, and calculates DTDT and DDDT over specific time windows.
And then you set thresholds, not just for temperature, but for these rates of change, too.
Precisely. You might program it to say, okay, if DDDT goes above X degrees per hour, send an alert. Or if DDDT is high and DDDT is also high, meaning it's accelerating fast, trigger the cooling system immediately.
So it could ping the farmer's phone?
It could, yes.
Yeah.
But even better, it ties directly into the barn's automated systems. That high DDDT calculation could automatically turn on fans, start misters or cooling pads, open vents, whatever the setup is.
And could it even prompt other actions, like suggesting changes to feeding times or checking water lines based on predicting when stress might peak?
That's exactly the kind of proactive management this enables. And looking forward, you can feed all this historical derivative data, along with animal performance records or crop health notes, into machine learning models.
To get even smarter.
Yeah, to refine those thresholds, improve the forecasting, make the whole system learn and adapt.
Okay, so wrapping this up then, it's really clear that these math concepts, the derivatives, DTDT, they're not just abstract stuff for a textbook.
Not at all. They are really vital practical tools. They give farmers those crucial early warnings and let automated systems react smartly, proactively to how the temperature is behaving, stopping problems before they really take hold.
And the payoff is huge. Healthier animals, more productive farms, maybe even healthier crops nearby.
Right. Plus, smarter energy use, better resource management. It adds up to more stability, more sustainability for the whole operation.
It really hammers home that point, doesn't it? That the calculus you study has real, tangible applications. Understanding and managing dynamic systems like the climate inside a barn or, the environment around it.
Absolutely. It's a powerful demonstration of that.
Makes you think, though, beyond barns and temperature,
Mhm.
where else could looking at the rate of change be really useful? Analyzing how fast things are changing in other areas. Maybe like urban traffic flow, or how information spreads online, or even economic trends. Could measuring the rate of change, the acceleration, give us crucial predictions there too? Help us spot issues earlier or optimize things?
That's a really interesting thought to leave people with. Where else does the speed of change matter as much or maybe even more than the current level? Lots to consider there.